So in this video we're going to look at graphs of motion. So from the subject outline from SACE, graphical representations can be used qualitatively and quantitatively to describe and predict aspects of linear motion. So you need to be able to use graphical methods to represent linear motion, including the construction of graphs showing position versus time, velocity versus time, and acceleration versus time. And we're going to need to be able to use these graphical representations, so these graphs, to determine quantities such as position of an object, displacement, distance, velocity, and acceleration. So we'll learn how to do these things over the next couple videos or so. So this is a video of position of an object versus time. Now this is a graphic of constant velocity, constant positive velocity. So it's an object that is moving at a constant speed away from some sort of position. So if something's moving at a steady velocity, it means we expect the same displacement, so change in position, over the same given amount of time. So say this is at 1 second, 2 seconds, so for every second the position of the object is changing by the same constant amount. So we can easily see that as time is increasing, displacement is increasing steadily. And as I mentioned, this shows an object that moves at a steady, constant velocity, and it's a positive velocity because it's moving to the positive direction. Now these are just some more distance time graphs. So distance time I'm probably going to use interchangeably a bit with position time graphs, because realistically it's just showing you the change in position, showing you that change in displacement or that distance travelled. So the steeper a gradient of a position versus time graph, indicating a faster velocity. So that displacement in time is changing much more rapidly, whereas this graph here is slower, because displacement's only changing a little bit with every given second, whereas here a lot we're being displaced at a faster rate. So the steeper the gradient, the faster the velocity of an object. Now these are just some position versus time graphs that are showing both positive and negative velocity. So on these two graphs previously that we just seen, this here is a positive velocity, but it's it's moving at a slower rate, whereas this object here was obviously moving at a faster rate. But the main thing is that they're both moving to the right, or forwards, or rightwards, and they both have positive velocity. Whereas these two down here have negative velocity. So remember, positive for us is moving to the right, okay? Whereas negative velocity means we are moving to the left. So this object here is starting at some position away from its origin. So say if this is its origin, starting, I don't know, let's just say it's 10 meters away, so the displacement is positive 10. So this object must be moving back towards its origin, which means if this is at position displacement of plus 10 to the right, it means that we must be moving to the left, because we're heading back towards our original point. I'll show you something called the running man to help us visualize this. But yeah, so this actually has a negative slope, or a negative gradient. So you'll notice from maths, especially, we've been talking a bit about positive gradients. So if something has a positive gradient, it's got a positive velocity. So if the line is sloping up and to the right, positive gradient, positive velocity. If something's sloping down and to the right, it's going to have a negative velocity, okay, a negative gradient. And again, if the gradient is really steep and negative, that means we're moving at a faster constant velocity. Whereas this one's less steep, it's a slower constant velocity, but to the left, because it's a negative velocity. Now we can have position versus time graphs. So we've only been looking at constant velocity. So if the line is nice and straight, it means that an object is moving at a nice constant velocity. So for every 1 second elapsed, this object is changing in position, so it's being displaced by 10 meters to the right. Every second that passes, 10 meters to the right. So it is a constant velocity. It's not a straight line. It signifies constant positive velocity. Now in this second graph, we have a line that is curved. So from 0 to 1 seconds, the object's only being displaced maybe a couple meters to the right, and then as another second elapses, maybe another 5 or 6, and then maybe another 10, and then maybe another 13, 14, and so on and so forth. So our velocity, our displacement over time, is actually increasing. So our velocity must be increasing, and if our velocity is increasing for every second, it means that we are accelerating. So this is a position versus time graph of an object that is accelerating with a positive velocity and a positive acceleration. So imagine this is someone that's building up towards their top speed in a 100-meter dash. It takes a few seconds to build up to that max speed. Now, with position versus time graphs, so in this here is an example of a negative velocity. Again, it's a curved line. Okay, so there's not constant velocity, there's some sort of acceleration going on. Now, imagine this is an object. So initially, its displacement, so its change in position, is really minimal. So it's not actually, so its speed is quite slow. And we know it's going to be negative velocity because it's a negative gradient. Now, as time elapses, what happens to this negative velocity? The line is getting steeper and steeper and steeper and steeper. So this is actually an example of an object undergoing negative velocity, but with also negative acceleration. So as it's going along, it's accelerating faster and faster in the negative direction. So this is an example of negative velocity with negative acceleration. Now on this diagram, this representation of position versus time, again it's negative velocity, but what's happening to the displacement? It's actually getting slower until it basically is coming to a stop. So this is an example of an object that has negative velocity, so it's moving to the left, but it's actually slowing down, which means that it must be accelerating in the opposite direction. So this is an example of a graph of negative velocity but with positive acceleration. Now it might be a bit confusing, but once you have a play around with a running man, hopefully these ideas start solidifying if you are a bit confused. So the main takeaways I want you to get from the following from this video are the following. So with position versus time graphs, now a horizontal line indicates an object is stationary. So there is no change in position over time, no displacement, it's stationary. Hope that makes sense. So stationary just means an object is not moving. Now the slope or the gradient of a line, that indicates the velocity. So if it's a straight line, we can calculate the gradient of the line, and that's going to give us the constant velocity an object is undergoing. So what you can be asked to do in a test is to calculate the velocity of an object from 0 to 5 seconds. So to calculate the velocity of the object, we're going to calculate the gradient of the line. So there's two ways we can do this. So the gradient of a line is equal to either the rise over run, or we can pick two coordinate points. So we'll just go with rise over run first. So if looking at this diagram, we have a rise, this line rises from 0 on the position axis up to 25 meters. So there's a rise of 25 meters and a run of 5 seconds from 0 to 5. So there's a run of 5 seconds. So it's 25 meters per 5 seconds. So that's going to give us a speed of 5 meters per second, which makes sense. So remember, just a quick calculation. So the distance of an object is equal to the speed it's travelling at, or the velocity, times by the amount of time. So if it's traveling at 5 meters per second for 5 seconds, it's going to travel a distance or a displacement of 25 meters. So that works with our diagram. Now the other way to calculate gradient is using the following equation. So m equals y2 take y1 over x2 take x1. Now the way I'd like you to do this is to pick two coordinate points. So this coordinate point here is 0, 0, and this coordinate point here is the point 5, 25. Now I want you to label your coordinates x1, y1 and x2, y2. Always label your coordinates from left to right. So plugging them into our gradient formula here. So y2 is 25, take y1 which is 0, divided by x2 which is 5, take x1 which is 0, and that's going to give us 25, take 0 is 25, 25 divided by 5, which is, again, 5 meters per second. Now, obviously rise over run is simpler, but the reason why I'd actually prefer you to do it using the gradient formula is because we're going to have lines that don't start off at the origin. So we're going to have lines that start off at random points, and they might be negative, positive, and it's a lot harder to visualize the rise over the run. So I'd actually prefer you to use the gradient formula to calculate the speed. Now, this is another example I want to go through. So we're going to be looking at the position of a walrus. So this is a displacement of position versus time. This is position. So position of the walrus. So determine the total distance walked by the walrus during these 9 seconds. So the way we do this is the following. So initially the walrus started off at 1 meter to the right of the origin. So the walrus has walked 1 to 3. So the walrus walked 2 meters. He then walked another 3 meters back to the origin. So he's walked a total of 2 plus 3. So he's walked, so S is equal to 2 plus 3, which is equal to 5 meters travelled. So determine the resulting displacement of the walrus during these 9 seconds. So displacement is change in position. So what is the change in position of the walrus? So initially the walrus started off at 1 meters to the right of the origin, and he's now found himself at the origin. So he's actually been displaced -1 meters from where he started. So his displacement over these 9 seconds is -1 meters. So determine the displacement of the walrus after 5 seconds. So where is the walrus at 5 seconds? He's here. He's at 3 meters. So his displacement, he's been displaced from here, 1 meter, up to 3. So his displacement after 5 seconds is 2 meters to the right, so it's plus 2 meters. Now, looking at the graph, part D, during what time interval was the walrus at rest? Now, a walrus will be at rest when his position is not changing with respect to time. So that's occurring from 4 to 6 seconds. So during what time interval was the walrus at rest? So from 4 to 6 seconds. Now part E, what was the velocity of the walrus during the first 4 seconds? So the first 4 seconds, from here to here, we've got the gradient of a constant velocity line. Constant position versus time line. So the velocity of the walrus is going to be the gradient of this line. So it is going to be, so the velocity is going to be the rise over run. So basically it's going to be, you can do it as rise over run. So it's going to be a rise of 2 meters over a run of 4 meters. So it's a rise of 2 over a run of 4. So it's going to be half a meter per second to the right. Now, what was the velocity of the walrus from 6 to 9 seconds? So from 6 to 9 seconds, the walrus, so we need to work out the gradient of this line. So now it's going to be rise over run again, but it's going to be a negative rise. So it's going to be -3, so our rise is going to be -3 meters over 3 seconds. So it's going to be -3 over 3, which is going to give us -1 meters per second. Or you could have said, no, let's leave it as that. And let's get rid of the arrow. Let's leave it as positive 0.5 meters per second. I like positive and negative better than arrows. So what was the, and it's important that we had negative because it's showing that there's a negative velocity. The walrus must be moving to the left at 1 meter per second. So it's much faster from 6 to 9 seconds. Now, what was the average speed of the walrus for these 9 seconds? Now, average speed, so the formula for average speed is distance over time. So the distance of the walrus, so how far did the walrus travel in total? So we worked it out on the previous slide, so he travelled a distance of 2 meters and then back another 3. So he travelled 5 meters in total. And it took him 9 seconds. So his average speed was 5 divided by 9, which is 0.55 recurring. 0.555 recurring. So we'll round that to 0.556 meters per second. Now, what was the average velocity of the walrus for these 9 seconds? So, average velocity is displacement over time. So, for these 9 seconds, the walrus was displaced. So, displaced from +1 back to 0. So, it's a displacement of -1 meters over the 9 seconds. And -1 divided by 9. -1 divided by 9 is -0.111, rounded to 3 significant figures, meters per second. So I now want you to do the following questions. So first in the booklet, the questions on position versus time, and then the textbook, and I might also give you the Moving Man worksheet. Thanks.